All right, so it's Thursday. We're almost through our second week, making progress, uh, getting closer to our first test. So, another reminder our first test coming up Monday. Um, we are going to finish up section 3.7 today. We started talking a little bit about this yesterday. We're going to finish up that first. I think we may have a little bit of time um, after we work a couple examples to maybe talk a little bit about chapter 4. We'll see how that goes. But that's the plan for today is to work some examples. Yesterday we talked about, let me try to remember, Hooke's law, um, Poisson's ratio, Hooke's law for shear, several things like that. And today we're going to try to apply those relationships and formulas that we discussed yesterday. See if we can solve some problems today. So, uh, anybody have any questions about anything before we start working on an example? We'll mention there's a couple examples in the book as usual. Strongly encourage you to look at those. Uh, but if no questions, we'll see if we can solve this problem first. Let me see. I may will draw the picture first. Again, it's a 3D picture, so mine may not turn out super great. We've got just a bar with the rectangular cross section, which is usual. I'm sure mine it will not be to scale. All right, so 1.5 inches wide, 2 inches tall, and yeah, mine's definitely not scale. It's supposed to be 3 inches long, but my picture definitely looks longer than 3 inches. This thing's made out of aluminum, and we are going to apply an axial force, compressive force, 8 kips. Not too bad a picture. It's just, again, a bar with a rectangular cross section. We're applying a compressive force of 8,000 pounds to this. We are asked or told that if I think the 1.5 inch side increases to, let me move this out of the way, 1.500132 inches. We want to find what is Poisson's ratio. Remember notation uses a lowercase Greek letter nu for Poisson's ratio, and also what the new length of the 2-inch side is. And we are given the modulus of elasticity for aluminum is 10 times 10 to the third KSI. All right, so we talked about modulus of elasticity yesterday. It's a material property. Remind you how it's determined or where it comes from is when you look at the stress strain diagram for a particular material, the first part of the graph is linear, and the slope of that linear portion is what we define the modulus of elasticity to be. So that's where that came from. Also pointed out, remind you that there's a table in the back of your book that's got material properties. So if we were not given that value for E, that's where you would go and look up in that table and get the value for the modulus of elasticity of whatever aluminum alloy you were given. So we got this bar, we're compressing it. Notice one thing we did talk about yesterday, that if you have an axial load or an axial deformation caused by that load, then if it stretches and gets longer, right, it's going to shrink and get shorter in the other two lateral directions. Whereas in this case, we're compressing this thing. It's actually going to get bigger in the lateral directions, and evidence the fact that we're told that this 1.5 inch side, this length here, increases. So it starts out 1.5 inches. When it's compressed, it increases to that value that's just over 1.5 inches. And notice also confirms previous discussions about, we're talking about really, really small deformations here. So be careful, don't round off too much. You can significantly affect the answers you get if you do so. All right, so I reckon first thing we're asked to find is what Poisson's ratio is. Again, if we're not specifically told what aluminum alloy it is, we don't have access to a table with material properties. And again, if we're not given the specific alloy, we don't have enough information to do it anyway. But we're given enough information to actually find what Poisson's ratio is, just from the definition of Poisson's ratio. Remember, Poisson's ratio is negative the lateral strain over the longitudinal strain. Remind you, the negative is put in there so that Poisson's ratio always comes out positive, because these two strains, lateral and longitudinal, are going to be opposite signs. One's positive, one's negative. So we put the negative there, so Poisson's ratio comes out positive. So it looks like if we can calculate what the lateral strain is and what the longitudinal strain is, then we just plug those values in, we get Poisson's ratio. Right? So that's the approach, the way we're going to attack this specific example. Well, the 1.5 inch side, that's one of the lateral directions. And so we know the change in length, and we know the original length. That's what normal strain is change in length over length. So I know the lateral strain is just the change in length in the lateral direction over what the original undeformed length was in the lateral direction. So to get the change in length, I just take the 1.500132, subtract the original length of 1.5, divide by the original undeformed length of 1.5, and that is my lateral strain. And let's see, what did I get? Looks like 4 zeros. 1, 2, 3, 4, 8, 8. All right, any question how we got the lateral strain? Now, to get the longitudinal strain, we don't have the information given to get the longitudinal strain using the same approach, right? We could get the longitudinal strain by taking the change in length divided by 3, but we don't know what the change in length is. But we can get around that if we make use of a couple other things that we do know. We do know normal stress, P over A. We know what the force is. We can calculate the cross-sectional area. And so we can actually calculate the stress excuse me, it's compressive. So I'm going to use the sign convention, positive tension, negative compression. And again, up to you if you want this to be in PSI or KSI, whether you leave the force in kips or convert it to pounds. It really, I suppose, doesn't matter a whole lot. We'll leave it in kips. So it'll be -8. Now the cross-sectional area here, it's just the area of a rectangle. It's 2 inches tall, 1.5 inches wide. So 8/3, 2.666. I don't know how. 2.67 probably be sufficient enough. But that's what the normal stress is in this aluminum bar. And now we know what the stress is. We know what the modulus of elasticity is. Here's where we can apply Hooke's law. Hooke's law gives us that relationship between normal stress and normal strain. Sigma equals E epsilon. Well, we know what E is. We just calculated what sigma is. So we can get the longitudinal strain. Right, just take our stress, it's a bad looking sigma, and divide by modulus of elasticity. So we got -2.667 KSI as my stress. E was 10 times 10 to the third KSI. And notice both of these are KSI. So as long as they're both the same, it doesn't matter if they're KSI or PSI. And let's see, where did I calculate that? I got that somewhere. Let's see. It's negative. I got 3 zeros and then 2, 6, 6, 7. Notice it's negative. It's getting shorter, right? The bar is being compressed. So my longitudinal strain is negative. Well, now I have both lateral strain and longitudinal strain. There's my lateral, there's my longitudinal. Calculate Poisson's ratio minus the lateral strain. 1, 2, 3, 4, 8, 8. Divide by the longitudinal strain, which is a negative 0.00267. And I got obviously a positive 0.33. Which also agrees with the discussion when we talked about Poisson's ratio yesterday. Yeah, when we were looking at that material property table, I pointed out that for most materials, Poisson's ratio should be somewhere around 0.3, maybe a little above or a little below. And that other than concrete, remember I pointed out concrete was different. But pretty much any kind of metal, we should get something in the ballpark of 0.3. So this doesn't guarantee that we haven't made a mistake somewhere, but it's a reasonable answer. If we had gotten 3.3 or 0.8, something like that, then that should send up a red flag that, hey, we messed up a calculation somewhere. All right, so we got the first thing that was asked of us. We calculated Poisson's ratio. Any questions about that? All right, so we've got another part of this problem we're trying to answer, and that's what's the new length of the 2-inch side. Right, we were given what the new length of the 1.5-inch side. Well, the 2-inch side is going to get bigger also, and that's what we're being asked to find. What's going to be the new length of the 2-inch side. Excuse me. All right, so we got Poisson's ratio, and we know from the definition of Poisson's ratio that it's a ratio of lateral strain to longitudinal strain. We also know that, assuming this bar is we're not told otherwise, is all aluminum. This was one of our other discussions yesterday. That again, if you're using the sign convention here, where X would be the longitudinal direction, and Y and Z being the two lateral directions, that as long as our material, our structure is all the same material, the strain is going to be the same in both the lateral directions. Does not mean the actual deformation is the same, but the strain would be. That ratio of change in length over original undeformed length would be the same in both the Y and the Z direction. And in this case, I reckon if you want to apply this coordinate system to our picture, the 2-inch side is the vertical lateral dimension, so that would be the Y direction. So we know what the lateral strain is. So if Poisson's ratio is minus the lateral strain, we don't need that. Let's go back and go here. I know the lateral strain, yes, the change in length in the lateral direction over the original length in the lateral direction. Same definition we used up here. Right, well, I know what the lateral strain is. I know this is 0.00088. I know what the original length is 2. I can calculate the change in length. So if I want the change in length of the 2-inch side, all I got to do is take the lateral strain and multiply it times the original length of that 2-inch side. So we know the lateral strain was 0.0004088. Right, the original undeformed length was 2 inches, and I got let's see, what did I get? 30176. These are inches. Right, that's just the change in length. That's how much the 2-inch side is going to increase. Right, we want the actual change in length, or the new deformed length, which we used this notation previously, call it L prime. That would just be 2 plus that. So it would be 2.000176 inches. That would be the new deformed length of that 2-inch side, which again, as we see, it's going to increase. It's going to get a little bigger. So good example, making use of knowing what the definitions of lateral strain are, Poisson's ratio, Hooke's law. Any questions about this particular example? Okay. Silence means no questions. So we will move on and work another problem there.
Can you keep it right there just 1 second, writing down just the last line?
Yeah, that's fine. Just speak up and let me know when you finish.
Yes, sir. All right, I'm done. Thank you.
You're welcome. In fact, anytime, anybody, if I go to, change the page before you're ready for me to do, speak up and tell me stop, and I'll be glad to wait a minute or two and let you get whatever it is you need to get. All right, so let's move on to a different kind of example. This one, I was smart and I copied the picture because if you were counting on me to actually draw this, it wouldn't have come out looking nearly as good as this. And so I wanted to make sure, the picture was really clear. So we'll take a couple of minutes and kind of go through and explain, exactly what this is, while also give any of you want to try to draw this picture or anything like that. This will give you time to do so. But what you'll see is we've got this steel, I don't know what you call it. It's kind of a C-shaped bracket looking thing. It's made out of steel, and we're assuming that it is, I don't know, I'm out of focus. Well, there we go. We're assuming that it is rigid. So that means that we're assuming that steel does not deform or change shape, right? When we apply the loads, it doesn't deform. We've got another, just a flat steel plate that is also assumed to be rigid, so it's not going to stretch. And that steel plate is attached to our C-shaped bracket here by making use of these two rubber pads. That's what the two darker, got out of focus again. Come on. Those two darker pieces are rubber, and it's bonded to the steel. So some kind of epoxy, some kind of strong glue is used to glue those rubber pads to the steel C-shaped bracket and our flat steel plate. So those are all attached. And we got the dimensions of the rubber pads. We've got the width of the steel plate, which is the same as the width of the rubber pad. And we're going to pull on that steel plate with a force of 250 newtons. So when we pull on this plate, the two steel pieces are not going to deform, but the two rubber pads with this rectangular cross section, they are going to deform. And they're going to deform in a shape that looks like this. This would be, if you're looking at that top pad, that's what it's going to look like. When you pull on that plate, we're going to create this shear stress between on the surface of the steel plate and the surface of that rubber pad. It's going to cause that rubber pad to deform into a shape something like this. And what we're asked to find, and we're given what G is. G, remember, is the shear modulus, or in this textbook, he calls it the modulus of rigidity. It's a material property. It's kind of like E, except for E is relates normal stress and normal strain. G, the modulus of rigidity, is used to relate shear stress and shear strain. So we're definitely going to use that somewhere here shortly. But we're asked to find three things. One, what is this shear stress, right, that's acting on the surface of that rubber pad? Right? That's what part A is asking for. B asks for the shear strain on that rubber pad, which in a minute I'll draw a new picture, but refresh your memory. Shear strain, right, that's that angle of distortion, gamma. Shear stress is tau. This angle here, that's what shear strain is. So we're going to calculate what that angle is. And then finally, the third part wants to know what's the horizontal displacement of the steel plate. Well, the steel plate can only move as far as the rubber pad is deformed. So basically this horizontal distance delta, that's how much the steel plate's going to move, right? So those are the three things we're after. And before we start doing any calculations, kind of draw sort of a quasi free body diagram, and I'm going to do this in 2D, because I can draw much better in 2D, and I think it illustrates what we're actually doing here. So here's my steel plate. All right, so this is my steel plate. Applying this force of 250 newtons. Right, well, there's going to be a shear force, V, acting on whatever that adhesive or that glue or epoxy, whatever it is, that attaches that pad, that rubber pad to that steel plate. There's going to be a shear force, V. Now, if we look at the rubber pad, right, if you look at this is the cross section of that rubber pad. Again, equilibrium, when you draw free body diagrams, hopefully you learn this in statics. When you go from free body diagram of one to the connecting piece, the force is the same magnitude in opposite direction. So whatever that shear force V is acting on that glue that's on the steel plate, it's got to be the same as the shear force V that's acting in the opposite direction on the rubber pad. And again, for the rubber pad, it's in equilibrium. You got the same force V is going to be acting on that top surface of that rubber pad as well. And the same thing's going to happen below. If you look at this rubber pad, you're going to have a shear force V in that direction on the top of the pad, and a shear force V, same magnitude, opposite direction, on the bottom surface of that pad. Well, just looking at this, you should be able to hopefully just tell me, if you're looking at this free body diagram here, the force has got to add up to 0. So V's got to be half of whatever P is. That's going to be 125 newtons. So this shear force V, it's got to be 125 newtons. Since it's kind of acting like sort of similar to, when we talked about single shear and double shear, this is basically behaving like a double shear joint. But does this make sense? Everybody with me? How I know the shear force V is 125 newtons. All right. Well, we could look at the bottom pad or the top pad, either one. Obviously, they're the same size and you got the same shear force. But for visualization purposes, I think maybe you can see it better if we look at the bottom. If we look at the bottom pad, and again, I'll attempt to draw this 3-dimensional picture. All right, so if this is that bottom pad that we're looking at, I know this is 50 millimeters. We know the height is 25 millimeters. I know the length is 80 millimeters. And so what we have is this shear force. It's acting on that top surface. Right? And we know V is 125 newtons. Right? So that is the shear force acting on the top of that bottom pad. And hopefully we remember shear stress, right, is V over A. So to get the shear stress, take our shear force V is 125 and divide by the cross-sectional area. Now, be careful with units. Typically, we want newtons per meter squared. Well, our force is in newtons, that's good. But if we just do 25 times 50, our area, or not 25 times 50, don't listen to me. All right, this is our area. So it's going to be 80 times 50. Those would be in millimeters squared. So I'm going to go ahead and convert to meters. So 80 millimeters is 0.08. Right, and again, this is 50 millimeters wide. So that's 0.05, I believe. I get my right zeros. So that gives me newtons, and here I got meters squared. And so it'll come out in pascals. And I got 31,250 pascals. Which previous examples when we did SI units, we got something in the millions and we wrote it as megapascals. But here it's not as big, which is a good thing because this is the shear stress on that rubber pad. And that material is nowhere near the strength of like steel or aluminum. And so it's not going to take as high of stress values anyway. So it's a good thing that did not come out as big as what we've seen in some previous calculations. Any questions how we got the shear stress on that rubber pad? Again, we did the calculation on the bottom pad, but the top is the same. They're identical. So we do one. It's the same on both. All right. No question on shear stress. All right. Now for shear strain, right? This was part A. So for part B, the simplest, easiest thing to do would be to use Hooke's law for shear. Just like in that previous example, Hooke's law relates stress and strain. Well, we know what the material property is. We just calculated the stress. So Hooke's law for shear says that shear stress is equal to the modulus of rigidity, G, times the shear strain, gamma. So we're solving for gamma. We just take the shear stress, which is 31,250, and divide by G. Now, G is 0.6, but notice these are megapascals. This is 31,250 is pascal. So that's times 10 to the 6 pascals. And then, again, do the calculation. Got 0.05208. And remember, that's an angle. If you want to write radians, that's fine. If you don't want to write radians, that's okay too. Because radians is a real number. It's dimensionless. So if you want to just leave it as a number, that's fine. So that's the quickest, easiest way to get the shear strain is by using the Hooke's law for shear. Any questions how we got that? All right, well, we have one last part of this, and that was to get how far does this steel plate move? Obviously, it's going to move to the right. What's the horizontal displacement? And so I mentioned a minute ago, that's got to be the same as the deformation of that rubber pad. However far that rubber pad gets distorted, that's how far the steel plate's going to move. So I'm going to come down here and draw a new picture. And again, I'm gonna draw a picture of the bottom pad. Again, bottom and top are the same. So when we look at the bottom pad, it's going to get distorted, deformed. Again, it's just like the top one, except the top one, again, is if you're pulling on it this way, it's going to get distorted and deformed in a shape that looks like that. The bottom pad's going to do the same thing. It's going to, again, we've got this shear stress tau that we calculated acting on that rubber pad. It's going to cause it to deform or distort like that. And this angle here is the angle gamma we just calculated. That is the shear strain. And what we are after is what is this horizontal displacement We'll call it delta. That's what he called it up there. And I know the vertical height of this H is 25 millimeters. That's how tall this is.
Hey, Mr. Walters, I have a question. For average shear stress, when you're calculating the area, why is it 0.08 times 0.08 instead of 0.08 times 0.05?
That's because I wrote the wrong thing.
Okay.
I think I said 80 times 50, but I have no idea why I wrote 0.08 twice. It's that surface area is it's 80 by 50 millimeters. So this is 0.05.
Okay.
So yeah. Again, anytime somebody sees something like that, you got to speak up and say something, because a lot of times when I go back and I'll see it and I'll catch it, but sometimes I don't. And so if nobody says anything, then somebody else might not notice and confuse somebody, and they'll think, well, how do you get that? Well, because it shouldn't be that. So yeah, that it should be 80 by 50. So 0.08 times 0.05 is the area, the surface area at the top of that rubber pad. And so yeah, I have another question asking, are we going to have to memorize the formulas? Yes, but we're going to talk about that tomorrow. And I think when you see it, there's only maybe about 5 or 6 formulas. There's not that many. And so, yes, for this first test, you're going to be responsible for knowing these formulas. All right. Well, we kind of discussed this a little bit when we first talked about shear strain, and that is, as long as we're talking about really, really small deformation, and I don't know what 0.052 radians converts to in degrees. If somebody's out there got a calculator and want to convert that to degrees and tell me, I know it's small, right? So I know we're talking about a really small angle here. And I told you we could use this small angle approximation. And that is that this angle is essentially equal to tangent of that angle. So when we look at this right triangle here, tangent's opposite over adjacent. So we'll just do it this way. So tangent is going to be opposite over adjacent. It'll be delta over 25. And we know what the gamma is. Right, this is 0.05208. Solving for delta here, we get that times 25. And I got 1.3. That's probably good enough. Millimeters. I guess these are millimeters. So whatever this is, that's millimeters. This is going to be millimeters, because again, the strain's dimensions. So that rubber pad is going to get distorted and move over 1.3 millimeters. That is exactly how far, the same distance that steel plate's going to move, 1.3 millimeters. So really, really small displacement there. Was anybody industrious and calculate what that angle is in degrees? If you did, speak up. If you didn't, somebody curious now. 3 degrees? Thank you, Zach. So again, that's a really small angle. Small enough that our small angle approximation is valid. If this had been 30 degrees, yeah, I don't know how much faith I put in this answer. Maybe we've probably gone beyond what's allowable there. Certainly if it was 45, 60, 70 degrees, then definitely worthless answer we got. Nowhere close to being accurate. But for 3 degrees, it's very accurate. All right, I think I got another one chiming in, even more precise, 2.98 degrees. So it's a small angle. And typically, if you want kind of a ballpark figure, if it's 10 degrees or less, you're probably okay. Right, but that is something to check and keep in mind. You know, if you're in the real world, if you were doing this, you would definitely want to make note that and make sure that if we're going to use this approximation, that it's valid. All right. Any question about this about this example? All right. So this is basically where this is where test 1, which you're going to take on Monday, is you're responsible for everything up to this point. Yeah, that's the cutoff point for what you're responsible for on test 1. All right. We've got just a few minutes left, and so I wanted to do one more thing. It shouldn't take but just a couple of minutes, and that is kind of show you where there's a formula that we're going to use in chapter 4, and it's actually kind of good review for the test, because basically that's what we're going to do is take everything that we've been talking about so far, and we're going to combine a couple things and come up with a nice formula. And so that's where we need to start in chapter 4. Plus, it'll show you again using this same formulas we've been talking about. All right, so I'm assuming unless somebody speaks up, I can good here. All right, so basically in chapter 4 to start with, we're going to go back and revisit axially loaded members. And so I'm going to draw a picture, and before I show you where this formula comes from, I'll ask you a question. So say this is some length L. Yeah, this is undeformed. So that's our undeformed length L. If we apply an axial load to this, and just for illustrative purposes, let's assume it's a tensile force, and we're going to actually stretch this thing. It's going to deform some length or some distance delta. So the question I want to ask, and y'all have to be willing to chime in here, is basically I want to know what factors, or what determines or affects the magnitude of delta. In other words, what things have an effect on how far this thing's going to stretch or compress? So you can either answer, chat, or chime in. I'll give you a hint up front. There's 4 different things. And so I was going to see if everybody, between all of you, if you could come up with what the 4 things are.
How big P is?
All right, so that's definitely one, the magnitude of the force, right? Bigger the force, it's going to stretch further or deform more. So that one of the more obvious ones, but definitely good. Anybody else want to chime in? Please. We get
Modulus of elasticity.
Say that again.
Modulus of elasticity.
Did you say the modulus of elasticity? Yeah. Okay. Well, I'd see in some.
Yes, sir.
Right. So the material, right? Modulus of elasticity. if this thing is steel, it's not going to stretch as much as if it was aluminum. Some materials are stronger than others. So we got 2 of the 4. Got 2 more. If somebody will give me another one, I'll do the 4th one. But so we got the magnitude of the force, the material,
The area?
the size, right? The size, right? The cross sectional area. If I've got a steel member, the cross section is 2x4. It's not going to stretch the same amount if I have a steel member, the cross section's 3x5. Right? It's bigger, it's stronger. It's not going to stretch as much. Right? So the magnitude of the force, the material, what's the size of the cross section, and the 4th one that somebody's Zach there mentioned heat. We're not talking about heat yet. We're going to get to temperature effects later, assuming temperature is constant. The other thing that would affect how much it stretches is probably the least obvious, and that is what the original length is. The length L. And that one's not necessarily quite as intuitive, but I can give you an example. Say if you took a 1 foot length of rope and pulled on it with some force, it's not going to stretch as far. If you took a 10-foot length of that same rope and pulled on it with the same force, it's going to stretch further. And so that one's maybe not quite as obvious, but those are the 4 things that are going to have an effect and determine how far it stretches. Now, where this comes from, this is where we'll stop, is right. We know normal stress is P over A. We know normal strain, right, is delta over L. So all we're going to do is take Hooke's law. So we know Hooke's law says normal stress is equal to modulus of elasticity times the normal strain. Well, if we take this, substitute in for sigma, take this and substitute in for strain, you get P over A equal to E times delta over L, and then solve for delta. It's real simple and straightforward where this formula comes from. We get PL over AE. And there's the 4 things that we talked about up here. Right? Depends on the force, depends on what the original length was, depends on the cross-sectional area, and it depends on the material. And so we're going to make use of this formula in chapter 4. Now, tomorrow we'll talk a little bit more about this formula and maybe work one example. That'll be the first half of class. And then the second half of class, we'll talk about the test. I'll kind of go through and, again, we'll go through and see, what formulas we've used and what formulas you need, any questions you might have. So come prepared tomorrow to ask questions, at least, again, the second half of class, and then I'll stick around after class for as long as is necessary. But that's where we'll stop today, is here. So questions about the anything, the examples we worked today, how we got this formula, where it came from, before I stop recording. Okie dokie, then that's where we'll stop today. As always, I'm gonna stop recording and give me a couple minutes if you've got questions. We can address it here in just a minute or two.